This is a solutions video for the worksheet Circular Orbits. This is designed to not only practice your um, circular motion, applying second law to circular motion, the definition of force of gravity when G is not constant, which is big G, mass 1, mass 2 over R squared, and applying how to we can use factor of change. So all these problems can be solved using factor of change. So I just want you to know that this was taken, I think I used Khan Academy's AP Physics course. So I only drew one picture, only cut and pasted one picture from that. And so you'll see it refer to some picture, but it's not there. So I'm assuming you can draw the picture or use this first one as an example. So number one, a satellite of mass m. So there's the satellite's mass. It's right here, mass. Orbits the Earth. So the Earth is in the middle. So there's the Earth. And it is a radius r. And they're going to refer to this as radius, but it is the distance between the two objects, the Earth and the satellite. That is the distance between their center of masses, and it also happens to be the radius of this orbit. So we can use that R value. An aerospace engineer decides to launch a second satellite. So we're going to launch a second satellite that is twice the mass into the same orbit. So you can imagine a second satellite here, and it has twice the mass, but it's at the same distance r away. Okay. How does the speed v of the heavier satellite, um, how does it change? Is it three times the it's double the mass. So is it twice the velocity? Is it one half the velocity? So I need to know. So the factor of change. So I'm just going to focus on the first condition, and I'm going to sum the forces inward on the first satellite, and there's only one force acting on that, and that is the force of gravity. I'm not on the surface of the planet, so I have to use the big G equation. It is equal to what am I summing the forces on? I'm summing the forces on the mass of that satellite, times the centripetal acceleration. Big G equation is defined as big G times the mass of the planet, which is Earth, times the mass of the satellite. There's the two. I'm going to define mass of the satellite, ms. I'm going to use ms all over this. Divided by r, they called it r squared, is equal to the mass of the satellite. And now I'm going to plug in a value for a sub c. We know it's v squared over r, or r omega squared. We're going to use v squared over r because we're asking for something related to v. Now, the original velocity they called v naught squared, okay? And I want to know what happens to that velocity if I change some things. So I'm going to solve for v naught. I'm going to divide both sides by the mass of the satellite. I'm going to multiply both sides by r, and that'll get rid of that r and one of those r's, and then I'll take the square root of both sides. V naught is equal to the square root of big G, mass of the Earth divided by r. And that is the equation for the original satellite's velocity. Why did I solve for velocity? Because that's what we're going to ask how it changed. So this is kind of my method for factor of change. All right, now I'm going to find the factor of change because I know that V new is equal to factor of change times the V old, which is V naught, okay? So now I'm going to use this equation, and I'm going to ask which for each one of those things, did it change? Did G change? No. Did we change the planet that we were circulating around? No, it's still mass of the Earth, so that's by a factor of one. And we kept it in the same orbit, and we find that it is the square root of one, which is one. So we know that the V new is equal to one times the V old. So the velocity of the new satellite that has twice the mass is the same as the new satellite. I'm sorry, the same as the old satellite. Why? Well, look, mass of satellites on both sides of the equation, and it cancels. It's independent of the mass of the satellite. Aha. Okay, that's a time saver, just so you know. Now, a satellite of mass m orbits Earth at a radius r. So the same scenario. Here's my Earth. Here's the satellite. Here I am at r. I have a tangential velocity v naught. I have a period t naught for this first situation. And then I'm going to do some things. Identical satellite. Actually, let me go ahead and put up here MS. That's the original one. We're going to have the same orbit, but we're going to go to a different planet that has 3/5 the mass of the Earth. Now, before I get into that, we want to know something about period. So I got to have an equation that relates period to all these things. So I'm going to make sure you know what period is. Period is equal to 1 over the frequency, which is equal to 2 pi divided by the angular velocity. So period t is defined as the period, which is also defined as the time for one cycle. And cycle in this case is one orbit, and it's usually in seconds. That is the unit for period, seconds. This right here is on the equation sheet, and so there is a relationship between period and its angular velocity. So I'm going to sum the forces around the, I got to make sure my volume is working properly. Yeah, I'm going to sum the forces around the satellite. It's only the force of gravity acting on it, and it's the mass of the satellite times centripetal acceleration, which is equal to mass of the satellite times omega squared times r. Now, I picked omega squared times r as definition of a centripetal acceleration because they ask questions about period. So I have a relationship between period and its angular velocity. Big G, mass of the Earth, mass of the satellite divided by r squared is equal to, now I'm going to look at t equals 2 pi omega, which means omega equals 2 pi over t. So I'm going to plug that in for omega, 2 pi over the period. I'm going to square it. I'm going to multiply times r. So here's omega squared. Here's the definition of omega, and I took the definition of omega and I squared it. Now I'm going to solve again. What am I trying to do? I'm trying to see how all these changes affect the period. So get an equation for period. So mass of the satellite doesn't matter. Rearrange all this for period. So I'm going to move. Actually, let's go ahead and distribute that squared just so you guys can see this for the first time. I got 4 pi squared t squared times r. Everything in the parentheses is squared. Moves t squared to the left. Move everything else to the right. Take the square root. T squared equals 4 pi squared r cubed divided by big G over mass of the Earth. Take the square root of both. So I find t is equal to the square root of 4 pi squared r cubed over big G mass of the Earth. Factor of change. So t new is going to equal the factor of change times t old. And they define t old as t naught. Factor of change. So now, what am I doing? I'm looking at everything underneath here, and I'm going to write whether or not it changed or not. The factor of change. Does 4 change? No, it's a constant. Does pi change? No, it's a constant. Does r change? Same orbit. R is the same. So I have 1 cubed. So I'll put 1 cubed there. I'll make that pi squared. 1 squared is 1. Does big G change? No. Does mass change? The planet is 3/5 the mass of the Earth. Now you can put 3/5 like this, but I do this because I don't like keeping track of all that. I'm going to divide by 3, and I have to put another division sign or 5, or just move that 5 back up to the top. Okay, divide by 3/5 is the same as multiplying times the reciprocal, and it's still underneath the square root. That becomes the square root of 5/3. There's the factor of change. 2t, the period new, is equal to the factor of change, which is the square root of 5/3, times t old, which they called t naught. There it is. It's A. Number 3. I'm going to go a little bit faster. See if I can find all my papers here. Okay. All right. Same scenario. Here's Earth. Here's my satellite. Here I am, R. I've got a tangential velocity. I don't know, like V naught. I've got mass of the satellite, and we're going to double the radius. And we want to know what happens to the tangential velocity. So we're going to sum the forces inward on the existing satellite, or the first scenario, which is the force of gravity equals the mass of the satellite times v squared over r. Pick that for centripetal acceleration because we're asking for something related to its tangential velocity. Big G, mass of the Earth, mass of the satellite, divided by r squared, mass of the satellite, v squared over r. Mass of the satellite is cancels, one of the r cancels, and we get v equals to the square root of big G, mass of the Earth, over r. Now, I want to know how some things that I'm going to do affect that velocity. So the factor of change, and I'm going to look at each one of those items. I'm going to put that square root in there. G is a constant. The mass, the same planet, is the same. The radius was increased by 2. So the factor of change is the square root of 1 over 2. That becomes this 1 over the square root of 2. Then I get V new is equal to the factor of change times V old, which equals 1 over the square root of 2 times V naught. And that would be B. Number 4. They're asking about period, so you're going to need things in angular speed. You have a situation where I have a satellite, and here's Earth, here's R, here's tangential velocity, here's the angular velocity. We have a relationship between period, frequency, and angular speed. We know that omega equals 2 pi over t. That is on your equation sheet. I'm going to sum the forces inward. Force of gravity equals mass of the satellite times omega squared times r. I need it in terms of angular speed because I got to get it in terms of period. Big G, mass of the Earth, mass of the satellite over r squared equals mass of the satellite. Oh, let's go ahead and plug in t, or get period in there. 2 pi over period squared times r. Solve for t. Make sure you square everything inside that parentheses. Mass of the satellite cancels. I get big G, mass of the Earth. I'm going to move that one of those r's over. I get 4 pi squared over t squared. Solve for t. T equals the square root of big... Nope, I can't do algebra evidently. 4 pi squared r cubed over big G, mass of the Earth. Yes, I could simplify. Don't need to. Factor of change equals, I'm going to pay attention to everything over here. Factor of change is equal to 4 stays the same. Pi stays the same. Square 1, it's 1. R. Did we change R? No. We are just adding mass. I don't even have to do all this. This is 1. And the mass of the Earth stayed the same. Same orbit, same R. Equals 1. T new equals 1 times T naught. I could have easily done that without the math because all I changed was the mass of the satellite, and it's independent of the mass of the satellite. Okay, 2 more to go. Nope, 3 more to go. We have something that we're interested in related to V naught. I have the Earth, I have the satellite, I have R, I have a tangential speed, I have an angular speed. Sum of the forces equals big G, mass of Earth, mass of satellite over R squared equals mass of satellite times V squared over R. V is equal to the square root of big G, mass of E, or Earth, over R, if one of the R's cancel. And what are we going to change? Just identical satellites, so they're the same orbit, but now we're going to go to a planet that is 3 times the mass of the Earth. Factor of change, square root 1. We're going to change the mass of the planet by 3 times, same orbit, square root of 3. V nu equals square root of 3 times V naught. D. We're going to find something related to period. We're going to change the radius. And we're staying on this planet Earth. No change in mass of the planet. Not sum of the forces. This is sum of the forces inward. Big G is big G, mass of Earth, mass of satellite, R squared equals mass of satellite times R omega squared. Mass of satellite times R times 2 pi T squared. We will get rid of mass of satellite. We will solve for T. T squared equals R cubed 4 pi squared divided by G mass of Earth. Did I got everything? T squared gets moved over, R cubed, yeah. So I got to take the square root, and then I get T equals everything in that square root. The factor of change equals R. Does R change? Yes, it changes by 3 times. 3, and don't forget, I got to cube it. Then 4 does not change. Pi does not change. Big G does not change. And we are still around Earth, so the mass doesn't change. So that's the square root of 3 cubed. The square root of 3 times 3 times 3. 3 times the square root of 3. T nu equals the square 3 times the square root of 3 times T old, which we called T naught. There's the answer. One more. We're interested in T naught. Let's look at it. Mass, first satellite's mass is M around a radius of R with a speed V naught and a period T naught. An aerospace decides to launch a second satellite, and we're changing the mass in the same orbit, and we did not change the planet. Answer C. It's independent of the mass of satellite. All right, that is